Welcome to the Overdose. This is Unit 1, Section 1 of Medical Physiology, and we'll be discussing the biochemistry and cell biology that is pertinent to physiology. We're going to start off pretty basic, but this will ramp up pretty quick. And Section 1.1 is going to be about body fluid. Before I start talking about body fluid, let me be clear by what I mean. So here I've drawn a donut, and in this donut we have a hole in the center. This hole is not actually part of the donut. It's just air that goes through the donut. Just like out here beyond the donut is all air. It's not actually part of the donut. And so this is how anatomists and physiologists describe our body as basically a big donut. We could draw a circle around this donut, and all of that would be external to the donut itself. So this center represents our GI system, our mouth, our intestines, our esophagus, all the way through our anus. That's considered the inside of the middle of the donut, and it's not actually considered to be inside of our body. It's considered to be external to our actual body. But all of our cells and all of our body, in quotes, that's all considered to be part of the donut. And so you can imagine if I have this cell, I have on the outside of the cell, I have one kind of fluid, and on the inside of the cell, I have another kind of fluid. These two fluids have different chemical makeups, and so they are considered to be two different kinds of fluids. But both of those fluids are considered to be within the substance of the donut itself, within our body. We also have other kinds of fluid that are gastrointestinal fluids, and I'm not at this time talking about those kind of fluids. That would be the center of the donut. Okay, so with that background, broadly speaking, we have two types of fluid. Extracellular fluid, or also called ECF, and we also have intracellular fluid, also called ICF. And within the extracellular fluid, we can break this down. We can break it down to blood, also called plasma. The blood is plasma plus the cells that live in it, and plasma is just the fluid and protein component of the blood. Then we can have the lymph. We have interstitial fluid, also called IF. And we have other things like cerebrospinal fluid. We have the fluid that's in the inner ear canal. And there's several other kinds of fluid that are not going to be focused on now. But these top three are the main three for an introductory physiology course. Now, oftentimes, lymph and interstitial fluid are going to be classified together because both of these have one hugely important thing in common. They are both considered ultrafiltrates of the blood. And so most of the fluid in your body is actually an ultrafiltrate of the blood. However, specifically, these are directly ultrafiltrates of the blood. Big differences between these two, though, are things like protein content and cellular content. Now you should know that the water is not split up evenly in these compartments. The extracellular fluid represents about 1/3 of your body's water weight, while the intracellular fluid is approximately 2/3. And you should also know that water, because it has a weight, it will contribute to your body weight. So let's go ahead and draw two triangles. Now on this side represents the percent of water weight, and this side represents the percent body fat. So what I'm depicting here, what I'm drawing here, is that as your body weight, so if this is your body weight right here, so this would be the relative amount on the x-axis, as your body weight goes from little to a lot, your percent water weight goes from a lot to a little. So they're inversely related. As the body weight goes up, the percent water weight goes down. And so what percent of your body is water weight? Well, it's usually approximately 50 to 70% of your body is made up of water. And so if you have a high percent body fat, then you would have approximately 50% of your weight as water. And if you have a low percent body fat, then you would have approximately 70% as water. So let's go ahead and draw a line, and we'll say that water has certain properties, and those properties make it great for what it does in making up life. So what are those properties? The first is it has a high heat capacity. Second, it has a high heat of vaporization. Thirdly, it has a high dielectric constant. And fourthly, it has a high surface tension. What does this mean for you? The high heat capacity means that you can add thermal energy to water and it won't change its temperature very much. So if you added, let's say, 1 unit of thermal energy to a piece of metal, its temperature would increase significantly. But if you add 1 unit of thermal energy to a little bit of water, its temperature will not change very much. That means we can go outside in the middle of the summer in the desert, and although we will warm up, we will not warm up as fast as we would if the fluid in our body was made up of something else. The high heat of vaporization means that we can go outside on a warm and windy day and we will not immediately dehydrate ourselves. It takes a lot of thermal energy for water to start evaporating, which means good for us, we're not going to get dehydrated easily. Third, the dielectric constant, basically that has two significance. First, it allows us to dissolve things, and secondly, we can conduct electricity. Now, this high surface tension gives us something that we call the hydrophobic effect. Let me explain this. First of all, I like to describe water as Mickey Mouse. So you see Mickey Mouse has these two big ears, and these big ears have sort of a slightly positive charge. These would be our hydrogens.
The electron on hydrogen likes to gravitate toward the oxygen.
Because it becomes close to the oxygen, this proton out here is a positively charged thing, and the negatively charged balancing is moving towards this oxygen, and the oxygen is slightly negatively charged. And so if we have another water molecule, you'll see that the negative charge on the molecule here would be attracted to the positive charge of this side of the molecule here. So the front of the molecule is attracted to the back of the other molecule. And so there's a slight hydrogen bonding interaction between these two molecules of water. So water likes to stick to itself. Now over here on the left, I've drawn what we describe as the membrane of a cell. So we have a phosphate head that has a negative charge. All these yellow phosphate heads are negatively charged. And so the positive portion of water likes to interact with those negative charges. However, the internal part of this lipid membrane, this is a phospholipid membrane, it is neutrally charged, so there's no charge at all. So water gets in here and it says, I'm not able to interact with you at all. I'm more attracted to what's going on out here. And so it moves back out. It doesn't go in and interact with these lipids, these hydrophobic parts. And so water is said to be attracted to itself. That is called surface tension. And because water is more attracted to things that are like it, things that are charged, anything that is uncharged, water basically pushes away. It makes something in biochemistry, it's called a Cartridge cage. You can go and look that up if you're interested, but it explains the entropy behind why this hydrophobic effect takes place. And so let's look at the notes. I say here that the body lives in a fluid environment. So we're talking about the body fluid because that's what all the cells live in. They're in and surrounded and absorbed by fluid. There's an external environment, the air. There's the internal environment of the GI system. It's the big donut concept. And so what is in the GI system is not really considered part of the inside of our body. So I say there's an internal environment of fluid that would be the extracellular fluid and the intracellular fluid, 1/3 and 2/3 respectively. And the extracellular fluid can be further classified interstitial fluid, lymph, plasma. 50 to 70% of your body weight is made up of water, and that proportion is inverse with the body fat. Why is our body fluid made up of water? Well, it has great properties. For example, surface tension, creating the hydrophobic effect we just talked about. A high heat of vaporization, so it's hard to dehydrate yourself. High heat capacity, so you have optimal heat transfer. This is true for both warm environments and cold environments. Hard to heat you up, hard to cool you off. There's a high dielectric constant, so we can dissolve things and we can conduct electricity, important for nerves and muscles. Okay, so here I say that the interstitial fluid is an ultrafiltrate. The interstitial fluid, the lymph, all of it is an ultrafiltrate of the blood. That implies, saying that it's an ultrafiltrate implies that there's something that's in the blood that's not in the interstitial fluid. So if there are different substances within each section of body fluid in my body, I need to be able to measure those substances, or at least talk about the measurements. And so the first thing we need to discuss is molarity. Now, describing molarity is sort of a tricky concept if you haven't had a chemistry background, so I'll try to do it quickly. Imagine if I had 1 gram of hydrogen atoms. Hydrogen has a molecular weight of 1 Dalton. So now imagine that I had 4 grams of helium. Helium has a molecular weight of 4 Daltons. So the number of helium atoms required to make 4 grams is equal to the number of hydrogen atoms required to make 1 gram. So another way to think of this is imagine that I have 10 bowling balls. So I have a 10 bowling balls, or let's say I have 100 pounds of bowling balls. And my bowling balls each weigh 10 pounds. Let's also say that I have 50 pounds of textbooks. And let's say that my textbooks, they all weigh the same, they all weigh 5 pounds each. You can see that by looking at the per unit weight and looking at the total weight, I can quantify using weight how many units of books I have, or how many units of bowling balls I have. And so if I look at the unit weight of Daltons and I get that amount in grams, that is called 1 mole. The actual number is 6.022 times 10 to the 24th. So there are 6.022 times 10 to the 24th hydrogen atoms in 1 gram of hydrogen. There are 6.022 times 10 to the 24th helium atoms in 4 grams of helium. Same number of atoms, just a different weight. And that number is called a mole. So we haven't explained what molarity is yet, but we've described what a mole is. There is another concept called an osmole. An osmole says I take a molecule and I put it in water. How many particles does it become? So if you take sodium chloride and you put it in water, it will actually dissolve and you'll get sodium with a positive charge floating around and chloride with a negative charge floating around, and these will be surrounded by water molecules, creating this cage because water can associate itself so that its positive charge faces all the chlorine and its negative charge faces all the sodium. And it can allow these two to dissociate from each other and become 2 individual particles. So the definition of an osmole is the moles of particles when dissolved in solution. So now let's say I have 1 mole of sodium chloride and I put it into a test tube and I fill that test tube up with water until it reaches the 1 liter mark. So you have to remember that whenever you mix things in water, you have 3 different concepts. You have the solute, you have the solvent, and you have the solution. So the solute is the particles that are being dissolved, the solvent is the thing that dissolves them, and the solution describes the whole thing. So I have 1 liter of solution mixed with 1 mole of sodium chloride. So that would be 1 molar. So we call it molar when we're describing molarity. So molarity is equal to the moles of solute divided by the liters of solution. And so we have described molarity. There is also something called osmolarity, and that describes the osmoles of solute divided by liters of solution. So moles and osmoles, osmolarity and molarity. Now there's a third concept, and that's called osmolality and molality. So molality, imagine that in this same test tube I put in my 1 mole of sodium chloride, but instead of filling it up to the 1 liter mark, I added exactly 1 kilogram of H2O. And so 1 kilogram of H2O is equal to 1 liter, but the sodium chloride also has volume, and so it's actually going to fill up to a little bit above 1 liter. Not much, but a little bit. So what that number is going to depend on the temperature and other things, but whenever you have those solutes, it will be a little bit more than 1 liter, but you know exactly the amount of water. In this other situation where we're talking about molarity, we don't know the exact amount of water, the solvent, we know the exact amount of the solution. And so that would be 1 molal, or we would say the molality is moles of solute divided by kilograms of solvent. So we're not talking about the kilograms of solution. We're not putting this thing on a scale and filling it up until the scale reaches 1 kilogram. No, we've already measured out 1 kilogram of water, and we are adding that to the solute. And just like there's molality, there's also osmolality. And so osmolality is osmoles of solute divided by kilograms of solvent. Now, we like to use osmolarity and osmolality in physiology because this describes how active, osmotically active particles are in the body. So if we can review osmosis, here we have the original U-tube. So in this U-tube, I'm going to put in some water. So I fill it up until the water level is here, and I have a semi-permeable membrane at the bottom. Now into this side, I'm going to dump some particles. And so I put a bunch of particles in here. And these particles have osmotic activity. And they will actually suck some of the water out of this side and put it into this side. And so the water level over here will go up. It went up by this much, which means the water level over here will go down by this much. And we can sit here and we can measure the height difference between these two. And you'll remember that water, you measure water pressure, the pressure in water is equal to the density rho times gravity times the height of the water. And so we can measure the height of this and we can determine what the osmotic pressure is. And as you'll see shortly, the osmotic pressure is directly proportional to the number of particles that I put in here. And so if I put in 1 mole of sodium chloride, then I would have sodium chloride breaking off into 2 moles of particles. And so it wouldn't be proportional to the moles of molecules I put in unless those molecules don't associate. So molarity isn't particularly great to use, neither is molality. But whenever I account for the total moles of particles, osmolarity and osmolality, it is directly proportional to the number of particles. Now that I've taken painstaking care to explain the difference between osmolarity and osmolality, I'm going to tell you that from now on, I'm going to use the terms interchangeably. Now, why do I use them interchangeably? Because water, 1 liter of water is equal to 1 kilogram. And when I take that 1 kilogram of water and I add in all of the proteins, all of the solutes, everything that you would find in something like plasma, you'll know is approximately 290 milliosmoles. And when I add all of those milliosmoles to that 1 kilogram of water, it is approximately the same volume. In other words, it's approximately 1 liter. But before I change subjects, let me explain how this is measured, how osmolality is determined experimentally in the lab. So if you took an ideal solution, if you had 1 mole of an ideal solute, and you put it in 1 liter or 1 kilogram of an ideal solution, then the freezing point goes from 0 Celsius down to negative 1.86 Celsius. Now this is assuming that the mole of the ideal solute doesn't dissociate. So if I had, in other words, it is 1 osmole. If I had 2 osmoles, let's say I had 1 mole of sodium chloride, then I would freeze it and I would find that the freezing point is actually negative 3.72. So the freezing point of 1 mole of sodium chloride is negative 3.72. If I take negative 3.72 and divide it by negative 1.86, I will see that that equals 2 osmolal. The osmolality is 2. Now in physiology, we typically measure things in milliosmoles. And so you could use a correction factor instead of dividing the freezing point depression. So the freezing point was negative 3.72, but we call it the freezing point depression. The freezing point depression was a positive 3.72, so it was depressed by 3.72 degrees. So I divide by 1.86, but the correction to change it to milliosmoles is 0.00186. And you would see that the sodium chloride, the 2 the 1 mole of sodium chloride, or 2 osmol sodium chloride, would actually come out to be 2,000 milliosmoles. And now when we take blood plasma, when you take plasma and you freeze it, you'll find that the freezing point depression is about 0.54 degrees Celsius. And if we divide that by 0.00186, then we would see that it is approximately 290 milliosmoles. And so the units on our 0.00186 is degrees per milliosmole. Okay, so concentration, we described what a mole is. A mole is a number of particles to get the molecular weight in grams. Osmole is the number of particles obtained when 1 mole is dissolved in water. So 1 mole of NaCl, 2 osmoles of ions, 1 mole of glucose, 1 osmole of glucose. So an equivalent is something I didn't quite describe. An equivalent is the amount of charge. It's the moles of charge. So when I'm talking about sodium, 1 mole of sodium is equal to 1 equivalent. But when I'm talking about calcium, a half a mole of calcium is equal to 1 equivalent, because there's a 2 plus charge on calcium. I explained the molarity is moles per liter, molality is moles per kilogram, and we're talking about solution versus solvent here. Osmolarity, osmolality, same thing, except you're dealing with osmoles instead of moles. Then pH. pH is a special way that we use to measure the concentration of hydrogen ions. If I were to measure the hydrogen ion concentration in molarity, anytime you put brackets around something, it typically means concentration in molarity. So if I were to measure the hydrogen ion concentration in molarity and then take the negative log of that number, that's what the pH of the solution would be. In other words, a lowercase p is an ancient mathematical way of saying the negative log. So let's look at 3 hypothetical situations, and suppose that I had a solution that was 10 molar hydrogen ions, a solution that was 1 molar hydrogen ion, and a solution that was 0.1 molar hydrogen ions. When all of this was originally being worked out, people used the log scale because it's easier to do math with logs if you know what you're doing. It's like adding 1 plus 1, I could be actually multiplying several things or dividing several things just simply by adding. And so log base 10 of 10 molar would equal 1. But we never ever, at least originally, we never ever had hydrogen ion concentrations at 10 molar. In fact, we would rarely ever see them get up to 1 molar. And so we would be looking at hydrogen ions in the 0.0001 molar range, and it sucks to use negative numbers, I suppose. So instead of using the log scale, we used the negative log scale. What does the negative log scale mean? So let me explain. Negative log base 10 of 10 is equal to log base 10 of 1 over 10. So the negative log is basically inverse of the fraction. So that the negative log base 10 is 0.1. Whenever I take 0.1, which is basically 1 over 10, when I invert that, I get 10 over 1. And so it is equal to the log base 10 of 10. And so the lower I go on the concentration of hydrogen ions, the higher my number will be. And so because P actually means, the definition of the lowercase p means negative log, the H stands for hydrogen ions, we say that pH is equal to negative log base 10 of the hydrogen ion concentration. There's another equation used to describe the pH called the Henderson-Hasselbalch equation. I'm not going to go into that here, that's for a chemistry lecture. It's also worth pointing out that physiologic pH, the pH of your blood plasma, is going to be roughly 7.35 to 7.45. Some textbooks will be even more precise and say 7.37 to 7.42. Remember that we said the osmolarity is osmoles per liter, so osmoles per liter, OSM, stands for osmoles per liter. Now osmolarity is equal to G times C. G, moles of particles, C, molarity of the thing. So if I said I had a molarity of sodium chloride, the molarity was equal to 1 molar, then the Osmolality would be G, the number of particles, 2 per mole, times C, which is the molarity 1, 2 times 1. I have 2 osmolar. We said that the freezing point depression can be used to determine what the molality is, osmolality. And so if I have a 1 molar concentration, it would depress the freezing point by 1.86. Now, osmolar and osmolal, roughly equivalent in physiology. And so if it depresses by 1.86 and we use milliosmoles, we can use the conversion factor of 0.00186. Now, plasma freezes at 0.54. 0.54 divided by 0.00186 is equal to roughly 290 milliosmoles. Okay, so let's take a look at this diagram. Right on the far left, I have the interstitial fluid. In the middle, I'm describing the plasma, and on the far right, I'm describing the intracellular fluid. And so what you'll see is I'll have positive charges on the left, negative charges on the right. You see that the positive charges and the negative charges balance each other out both within a given fluid and across different fluids. So there's approximately equal number of positive charges in both the interstitial fluid and the plasma, approximately equal number of negative charges in both the interstitial and the plasma. And you'll see that also the osmolality, I've described the positive charge as being slightly more than 140 and the negative charge as being slightly more than 140. You add that together, you get approximately 290 milliosmolal for the interstitial fluid, as well as for the plasma, as well as for the intracellular fluid. And so we say that there's osmotic balance between the various fluid compartments. We also say that there's charge balance within and between the various compartments. Now, these ideas are basic ideas. They do have exceptions. For example, the osmotic balance, you have osmotic gradients within the kidney, and you also have Starling forces which take place in the precapillary arterioles and the postcapillary venules. Those we'll talk about later, but as a general concept, you'll need to know that there's osmotic balance within the body. You also need to know that there's charge balance. There's also exceptions to this. For example, you have a membrane charge. You have a charge on the membrane, and that happens within the nerves. It happens within the muscles. But the charge is even there, the difference is so small that it barely violates this rule of thumb. And so it seems like I'm saying that all of these fluids are basically the same. What I want to point out now is the differences and some of the other similarities and differences. You'll see that from the interstitial fluid and the plasma, sodium is approximately the same. Chloride ions approximately the same. Bicarb approximately the same. What is different? Protein levels are the biggest difference between plasma and interstitial fluid. Protein gets trapped within the plasma as fluid is being pushed out to make up the interstitial fluid. It's called an ultrafiltrate. Then let's look at the intracellular fluid. So we look at sodium intracellularly and sodium in the plasma, huge difference. Potassium, huge difference. Calcium, almost all of the cellular calcium is stored in the endoplasmic reticulum. So when we talk about the cytoplasm, it's almost absent in the cytoplasm. Then we look at the negative charges. Chloride ion, really low. Bicarb, you could say it's about half, almost the same. Protein's a lot higher in the cell than it is in the plasma, and it's even more higher than it is in the interstitial fluid. Then you have this extra group of things called organophosphates. There are some organophosphates found in the plasma, but by and large, organophosphates are in the cell. And this is just not one thing. This is a group of several things. Anything that can have a phosphate head attached to it, either as an energy transfer or as an activator or as a signal transduction, when phosphate is used to store energy and send signals. And all of that takes place within the cell. Now, important concepts. Osmosis, we said, it describes the movement of water relative to a cell. So we can use terminology such as hypertonic, hypotonic, isotonic. So these are qualitative descriptions. There is quantitative description, which is osmolarity and osmolality. The quantitative description is a little bit better because it tells us what is responsible for this osmosis. Particles are being described, and that's what's responsible for the osmosis. And we said that if we used that U-tube, the original U-tube, remember, a tube that's shaped like a U, and we filled it up with water, and we used a semi-permeable membrane down here at the bottom, that we would have water on one side going up to here, water on the other side going to here, and we would have a height difference, and we could use that height difference to determine what the osmotic pressure is. And fortunate for us, there's also an equation called the Venthoff Equation. Now remember earlier we described what G times C is? G times C is osmolarity. And you'll remember that osmolarity is osmoles divided by liters. Now, sigma is something called the reflection coefficient, and basically what that describes is this. Suppose that I have a semi-permeable membrane here, and I have three different kinds of particles in it. I have really small particles, I have medium-sized particles, and I have large particles. Now, you'll know that whenever I have a small particle, it can freely move through that semi-permeable membrane. In other words, it's going to operate under diffusion. It will go through, it will not be kicked back at all, it goes through freely, it will have no osmotic pressure. On the other hand, I have these medium-sized particles, and they could come over here and they could interact, and they might squeeze their way through, or they might get pushed back. Okay, so in this case, we'll say that this one has a 50% chance of going through. It could be less, it could be more, but in this case, we'll say it's 0.5 or 50%. 50% chance of going through. And then this larger molecule, there's no way it could ever squeeze through. It's going to move over and it's going to get bounced or reflected back. So its reflection is 1 or 100%. And so the reflection coefficient sigma, it's a number that ranges from 0 to 1, reflecting percent, so 0 being 0%, 1 being 100%. It represents how hard it is for a particle to move through. And so if it's not hard for a particle to move through, the reflection coefficient is 0. It gets reflected back 0% of the time. And you know, anytime you multiply by 0, the whole thing turns to 0. And so if it can go through freely, then the osmotic pressure is 0. On the other hand, if it gets reflected back 100%, then anything times 1 is that thing, and the reflection coefficient just drops out of the equation. Whenever it gets reflected back 100%, then pressure is equal to Gc times RT. Now let's take a second and just look at that, but first, R, remember, would be the gas law constant, 0.082. And T would be the absolute temperature in Kelvin. So when we're talking about body temperature is said to be about 37 degrees Celsius. That is 310 degrees Kelvin. And body temperature doesn't change that much. So this whole term, R times T, is considered to be roughly constant. And if you want a number to put on that, it's roughly about 25.5 at physiologic temperature. Now I want to inspect this equation a little bit closer, imagining that the reflection coefficient is 100%. We said that G times C is the osmolarity, and that is in osmoles per liter. So remember, osmoles is the moles of particles. Remember, moles back in chemistry was described with the letter N. So the moles of particles times the gas law constant times the temperature divided by the volume. Remember, osmolarity is osmoles divided by liters. This is equal to the pressure. Now, if we multiply both sides times the volume, then we get that the pressure times the volume is equal to the moles times the gas law constant times the temperature. This might look like another equation that you learned in your chemistry class called the ideal gas law. And so what I'm trying to say is, don't try to remember a whole bunch of brand new equations. Just remember what you already know from chemistry. Remember the ideal gas law, and then add another variable called sigma, which is the reflection coefficient. And you can say that the osmotic pressure, P or pi, is equal to moles of particles times RT divided by V. Multiply all of that by the reflection coefficient, sigma, and that is your osmotic pressure. Let's try to put all this into clinical context. So I say here that some isotonic fluids become hypotonic after metabolism. Let's take a look at two different fluids. One would be normal saline and one would be 5% glucose. So anytime you have 0.9% saline solution, it's called normal saline because it is approximately 290 milliosmoles. And anytime you have 5% glucose, it's just called 5% glucose, but it is also approximately 290 milliosmoles, so it would be isotonic to your blood plasma. So you'll know that whenever you get a bolus of normal saline, it comes with some sodium particles and it comes with a bunch of water that it's dissolved in. If one of those sodium particles were to go away, that water would still be there, and so the tonicity would become hypotonic. It would have the same amount of fluid but less particles in it. Fortunate enough for us, that doesn't happen. There's not a very high sodium content within the cells, so the normal saline solution tends to stay isolated in the blood plasma. On the other hand, when you have glucose, what happens to glucose? Well, let's say that I have my glucose molecules and they are dissolved in water, and then I have over here, I'm going to use red, I have a red cell, and what happens is the glucose will go from extracellular to intracellular, and when it is inside of that cell, it will get phosphorylated, so a phosphate group gets attached. I'm hoping that shows up well, it's yellow, and when the phosphate group is attached, that is a chemical reaction, and because it's a chemical reaction, this is no longer glucose, it is called glucose 6-phosphate. And now that that is no longer glucose, there is no longer a glucose gradient within the cell, and so more glucose can move into the cell. And that more glucose can get phosphorylated as well, and that will become glucose 6-phosphate, keeping the glucose concentration, the actual glucose itself, the concentration of glucose in the cell is very low, but so it will continue to move into the cell. However, what happens to that water? The water does not move in as quickly, and so you have this hypotonic solution out here because we're going to erase all these particles that have moved in. We have just a few particles left. Now it's hypotonic. Although this effect isn't typically fast, and although it isn't typically a large effect, the effect does exist, and it's something that you need to be aware of clinically. So let's suppose you're working in the clinic and somebody gives you the blood chemistry of a patient. You can actually take the blood chemistry and calculate what the osmolality of the blood should be. So what should it be? So remember we said that there's a charge balance. So anytime I have a positive charge, which within my blood plasma, the largest portion of positive charge is going to be due to sodium. Anytime I have a positive charge, I have some other negative charge balancing it out. So that's 2 particles. So if I take 2 times the sodium, I add in 0.055 times the glucose, plus 0.36 times the blood urea nitrogen. I should point out that sodium is in milliequivalents per liter, glucose milligrams per deciliter, and BUN or urea in milligrams per deciliter. But 0.055 times glucose, 0.36 times the blood urea nitrogen. Add all that together, you should have within about 6 milliosmoles what the person's actual blood osmolality is. Now let's suppose you told the lab, I want you to measure the osmolality, and they measure it by freezing the plasma. They send you back, let's say they send you back and they say that the blood osmolality is 310, but when you calculated this up, you got that it was 289. So if the difference is greater than 6, as it is here, that tells you you should be looking for something that is not on your blood chemistries. Usually it's going to either be a toxin or alcohol. In other words, there is a missing piece to the puzzle.